react to the values of the signal at the inputs. Whatever input you'll give, combinational circuit will perform some function. The function on which the combination circuit has been built, and it will give you some output. So not necessary that number of inputs and number of outputs must be same. This is the block diagram of the combinational circuit. Just a minute, I'll start recording. Okay, fine. Yeah, so moving on to the next slide. So we almost use this combinational circuits every day. Like our mobile phones, our laptops have many of these combinational circuits. They are extensively employed in the ICs, in the integrated circuits, and these are referred to as a standard components. You may not know, but your laptops and phones may have millions of these combinational circuits. Even the microprocessor in your laptops contain millions of combinational circuits. Then let us see what are the canonical and standard forms. Yeah, so we'll learn about mean terms. What are mean terms? So this is a standard truth table where you have binary forms, binary numbers. Like this, this is a standard truth table where the binary numbers are written from 0 to 2 to the power n, where n is the number of variables. So if you have 3 variables, you'll have 8 terms starting from 0 to 2 to the power n minus 1, where each of this particular term will represent a corresponding decimal number. Like this is 0, this is 1, this represents 2, this is 3, and so on till 7, which is 2 to the power n minus 1. Okay, so what are the mean terms? We represent, to represent a mean term, we represent 0 by the complemented form. For example, if you have x and if its value is 0, we'll represent it as x prime. Similarly, for y and z. So here you have x prime, y prime, and z prime. Whenever the value is 1, you won't complement it. You will write it as the variable itself. So whenever you have 0, you will complement the variable. Whenever you have 1, the variable will be the same. Now, mean term is like we get a mean term by taking add and operation between these 3 variables. So like yesterday we saw the Boolean equation for AND gate was x into y. So for 3 variables, it will be x into y into z. So over here, where we have literals, like all the literals as are equal to 0, we'll have it as x prime, y prime, and z prime. And taking AND, we'll get x prime dot y prime dot z prime. This is the first mean term. Now, how do we represent this mean term? Mean term is represented by small m with a subscript at j, where j is the decimal equivalent of this binary number. So as I told before, this is 0. This is equivalent to 0. So you'll have the mean term as small m with a subscript as 0. Similarly, if we take some random example like this, 101, whose decimal equivalent is 5, you'll find that x is 1. So the literal will remain as x. Y is 0. So it will convert into prime. We'll take complement of y, which will be y prime. And z is 1. So that will be z. So taking AND between the 3 variables, you'll get a x, y prime, z. How do we represent it? We'll represent it with m, small m, with the subscript as the decimal equivalent, which is 5. So m5 is basically x, y prime, z. So you'll have you'll have 2 to the power n min terms corresponding to each term, where n is the number of variables. Like if you had 4 variables, you'll have 2 to the power n, which is 2 to the power 4, 16 min terms, which will go from 0 to 15. Now let us see what are the max terms. Yeah, so mean terms is called as a standard product. Why standard product? Because we are taking the product of the literals. Similarly, let us see what are the max terms. Max terms are called a standard sum. So here, this is like making a standard truth table where binary, like where this binary numbers will go from 0 to 2 to the power n minus 1. We are taking 3 variables, so we'll have it from 0 to 7. Now, max terms, when to obtain a max term, what we take is when we have the value as 0, we won't complement it. It will remain a if we have 0. When a will become 1, we'll complement it. So there is a difference between mean term and max term. In writing mean term and max term, in mean term, you will complement when it is equal to 0, whereas in max term, you will complement it when you have it as 1, equal to 1. So here, when the value is equal to 0, like when the decimal equivalent is 0 as well as binary are 0, 0, 0, corresponding to a, it is 0, so you write as a. Similarly for b and c. And max term is obtained by taking an OR function between the 3 variables. So you'll get it as a plus b plus c. Now how do we represent it? Just like mean term, we represented it by small m. Over here we'll use capital M with a subscript as decimal equivalent of this, or a decimal equivalent of ABC. Okay. Now expressing the Boolean function by mean terms. So if this is a function f1, if you have some function f1, which is equal to 0 when you have xyz as 0, as equal to 1 when you have inputs as this, and so on. Now you want to find what is this function f1? What is this function f1 in terms of xyz? How will you find? So there is a method for this. First spot all the ones that are in the f1. Find all the terms where the function is equal to 1. So in this example, you'll see it is equal to 1 3 times. So here, here, and here. Write a mean term corresponding to this term. Like for this, mean term will be x prime, y prime, z. Corresponding to this, mean term will be x, y prime, z prime. And corresponding to the last term, it will be x, y, z. And take an OR function between this, between these 3 terms. So you will get f1 as x1 prime, y prime, z plus xy prime, z prime plus xyz. Now, as I said that, like you can represent this as m1. We are using it in the terms of mean terms. So small m with a subscript as 1, because it's this decimal equivalent is 1, or this term is basically m1. So basically you will get m1 plus m4 plus m7. Now there is a standard or a brief notation to write this m1 plus m4 plus m7. What we do is we'll write this as summation of f1 as a function of x, y, z will be written as summation of, we'll just write this subscripts 1, 4, 7. This is a brief notation to express the above Boolean function. So for example, if you are given this as the function and you are asked to draw the truth table, you will just first write this xyz you'll just write the standard truth table for this, and then you'll put you'll put 1 at these places, and apart from that you'll put 0. So the summation symbol is basically to represent this OR. We are basically uh, doing an OR operation between these three mean terms. So the summation will represent that OR function. Now, what if I want to find f1 as a function of x comma y comma z in the terms of max terms? To get a max terms, you first find the complement of f1. So how will you find a complement? To find a complement of f1 from the truth table, take the min terms of those values where function f1 is 0. So it is 0 at the 0th place, second, third, and so on. So write the mean terms of all these terms where the function f1 is 0. You'll get this. So this is equal to f1 prime. Now you have to find f1. The question is to represent f1 in terms of max term. You got f1 prime as a in terms of mean terms. Now you want f1 in terms of max term. Complement the whole function. Complement on both the side. Yesterday you learned about the complement. What complement does is it will convert the AND function to OR and OR function to AND. So taking complement, you will get f1 this side, and this side you will get like like each and every literal will get complemented. Along with that, you will along with this plus, I mean this OR will get converted into AND. So this is what you will get. Now we saw like this converted into the form of x plus y plus z, which is nothing but or it's nothing but an OR function of this literals. So you can represent this in terms of max terms. This is m0, this is m2, this is m3, and so on. So you'll see that f1 as a function of max terms can be written as m0, capital M0, m2, m3, and so on. This is expressed as pi of 0, 2, 3, 5, 6. Why pi? Because we are doing an we are doing an AND operation between this 5 max terms. So this thing, when f1 is represented in terms of mean terms, it is called as sum of products. You are basically doing sum between the products. And when you when you take the when you write f1 as a function of max term, this is called as a product of sum. Basically, it is product between the sums. Okay, now conversion of a canonical forms. Boolean functions expressed as a sum of min terms or product of max terms are to be in a canonical form. So these are the two canonical forms. This is the first canonical form where you are representing f1 in terms of mean terms, and this is the other canonical form where you are representing f1 in terms of sum of product of sum. So sum of product, which is SOP, and product of sum, which is POS, are two canonical form. Now how do we interconvert between these two? What if I have SOP given and I want to convert into POS? So both of them are the complement of each other. The complement of a function expressed as a sum of min terms equal to the sum of min terms missing from the original function. So if you see, you have you have this thing going from 0 to 7. Okay, when if you see this, when you're representing it in the terms of min term, you have 1, 4, 7. So this is SOP. Okay, when you look for POS, you will find pi. So summation gets converted into pi, and find the missing terms from 0 to 8, 0 to 7. Find those terms which are missing. So basically find those terms apart from 147. So we'll get 0, 2, 3, 5, and 6. So this is how you get SOP and POS from each other. Like if you're given this, you can find this just by just by writing this sigma as pi, and uh, find the missing terms. So let us take another example where f is a function of a, b, and c, where the summation of which is sum of products of 1, 4th, 5th, and 5th, 6th, and 7th mean term. Now I want to find pi of this. This function has a complement which can be expressed as f complement as 0, 2, 3. Okay. Now, if we take a complement of f by De Morgan's theorem, we obtain f in a different form. So f is equal to, if we take a complement of this function, we get this m0 prime, m2 prime, and m3 prime. So complement of m0 prime is capital M J. I mean, when the subscripts are same, then max term and min terms are complement of each other. So how to get from here to here is just to write pi instead of sigma, and just to find the missing terms. That is the max term with subscript j is complement of the mean term. So basically using this property you can write. Now what are the standard forms? This was a canonical form wherein each term consisted of 3 literals. It had all the variables that we used as an input in the truth table. But what are the standard form? Standard form is basically other way to express the Boolean function, wherein the number of literals may be less than the total number of total number of inputs. For example, this is a standard form. Now you may ask, how do I get a standard form for this function, So yesterday we saw a table which had a properties of the which had the Boolean properties. So using the Boolean properties, you can actually reduce this in such a way that you get less than 3 literals. So unlike canonical form, which must have 3 literals, which must have all the literals or variables, either complemented or uncomplemented, standard form can contain any number of literals. Yeah, so Jairam will take the K-maps. K-maps will help you to reduce the, it will also give you the standard form of the Boolean equation. So I'll hand over to Jairam.
Hello everyone, myself Jairam. I'll be starting with K-map. Start to share my screen. Hope my screen is visible. So I'll start with K-maps. Okay, so what are K-maps? So K-maps are a pictorial representation to make a Boolean expression easier, to find the Boolean expression easier way. So we'll be using K-maps to find if we have a function or a truth table, we can use K-maps and we can find the expression for that function very easily. So we'll start with the so we have this website called 32xsite, which if you give the truth table or a function for the function, it will give the boolean expression very easily using K-maps. So you can try this website out once I teach K-maps. Yeah. So starting, we'll go start from two variable K-map. So if you have two variables, say x and y. So x and if x can take 0 and 1, y can take 0 and 1. So if there are two variables, we know that there can be four possibility, right? So x can be 0 1, y can be 0 1. So there will be four min terms. There will be four min terms. So we have to arrange this in a square fashion. We have to make every min terms as a boxes and arrange them as a square pattern. So taking x as like every row, say first row will be x will be 0 and second row will be x is equal to 1, as you can see in the image. And the same way, first column will be y is equal to 0, second column will be y is equal to 1. So if you take the first box, this box, you can say that x is equal to 0 and y is equal to 0. And if you take this box, x is equal to 0 and y is equal to 1. So you can make this boxes as the truth table is arranged in a box square fashion. Yeah. So first box represent M0, second box represent M1, and third box represent M2, fourth box represent M3. So we can say that if there is a 1, say if x when x is 0 and y is equal to 0, the output is 1. Then we represent this output as x dash y dash, right? So when x is 0, like if only if x is like x dash is 1 and y when y is 0, y dash is 1, if you multiply them, we'll get a 1, right? So when we have to see the values of x and y, if it is 0, put x dash, if y is 0, put y dash. So this min term will be corresponding to x dash y dash. So this is what we were doing in the SOP form, right? So we'll be simplifying this further by combining two or four or eight boxes. We'll get to know this. So this is how we draw the K map. So for two variable, first draw a box like and arrange the min terms m0, m1, m2, m3. Then we have to write the output. Say we take an example, f is equal to m1, m2, m3. So when what does this function mean? This means that m1 is equal to 1, m2 is equal to 1, and m3 is equal to 1. Like in this boxes should be filled with ones, and m0, there is no m0 in this function, right? So this will be 0. So we can say that we can arrange ones and zeros in this fashion. So you can understand, right? So m00 is 0, 01 is the m1, so it is 1. So 1 is like this is that's it. So f physically m1, m2, m3. So m1, m2, m3 should be filled with 1. So now we have for moving forward, as I said, this correspond to x dash y dash. This correspond to x dash y because x is 0 and y is 1, right? So this correspond to x dash y and the remaining is same. So this is going to be x y dash and this is going to be x y. But to make it simple, now what is the procedure of doing this K maps is we are going to combine in two ones. So we have first step, we have to check if there are four ones, but there are no four ones, right? So we have to combine two ones, two horizontal one or two vertical one. We can combine these two vertical ones. So we will put a box on this one, and but then this one is not combined with anything, right? So we will be combining these two ones. So this one is covered by this box and this box. There will be two boxes. So why what is the use of putting these boxes is, say if this I said this box will be represented as x dash into y, right? Because y is 1, x is 0. So x dash into y will give this representation of this box, right? And this will give x y. So in SOP form, we'll be finding every term and we'll be adding it, right? So this will give x dash y, this will give x y. On adding these both, x dash y plus x y is just y, right? So like if x dash y plus x y, if you take y common, y into x dash plus x will come. But like x plus x dash is always one, right? Like if there is an OR gate and one of the input is 0, one of the input is x and other input is x dash, the OR gate will always give 1 because at least one of the inputs will be 1. Uh, so this box, we can combine this box and see what is constant in this boxes. You can see that x is changing from 0 to 1 in this box, right? But y is still constant. So we can write the simplified form as y. We'll just write y for now, and then we'll like, so if you take this box, we'll get if we can see that x is changing, y is constant. So write y and take this box. in this box x is constant and y is changing. So if you just take this both term individually and add it out, we can say that we can the y plus y dash will get cancelled out and we will get just x. So like the simple method is put the boxes, check what is constant in the what is constant in the both the boxes. We can see that y is constant, write y, and another boxes check what is constant, x is constant, so write plus x. So the function is x plus y. We writing x because x is equal to 1 at this point. If x is equal to 0, say the 1 is here and we are combining this way, so we will have to write x dash because x is 0, right? So that time the function will be y plus x dash. So this is how we do for a two variable k-map. So then moving on to three variable k-maps, this is similar to two variable k-maps, but the difference is we have three variables and we cannot like we represented xy as square of x and y and the rows and columns, but we will be taking x as the rows and y is it as the columns. So because we have three variables, right? So y is it we can write 0 0 0 1 1 1 1 0. The important catch here is like we will be writing x as 0 1, y 0 0 0 1 and 1 1. Usually we'll be writing 0 0 0 1 1 0 then 1 1, right? So here will there's a change that 0 0 0 1 1 1 1 0, so that like if you see the min terms 0 0 0, like there are three zeros, right? The decimal equivalent is 0, so m 0 0 0 1, right? That is 1 0 double 1 double 1 represents 3, right? So it won't be like m0 m1 m2 m3, it will be like these two columns will be interchanged, m0 m1 m3 m2. So if you want to know why are we why is this both interchanged, after 0 1 1 0 should be there. If you ask that way, the simple explanation is on moving, say we are in this box, okay? So from this box we are moving to this box, we can see that only one variable is changing. So here z is 0 and here z is 1. On moving to one from one box to another, we can see that only one variable is changing, and from here to here we can see that only y is changing from 0 to 1. But if these two columns are interchanged, after 0 1 1 0 was there, we can see that y and z both are changing, so we will be having 1 1 in the third column. So this is why we write m0 m1 then m3 then m2, okay? So hope you understand. So so we have to write m0 m1 m2 on the rightmost, then m3. The same way after coming here m4 m5 m6 is written here and then m7. So this is how we write the table for the k maps. So the k maps for three variables. So first step for any question, like if there is an truth table of x y z and output is given on their own, so there's a function and the output is given, but we have to find the boolean expression. First we have to draw this k map. So first we have to draw this table, and as I said, x is represented here, y z is represented here. Keep in mind that m0 m1 then m3 and then m2. So this is the way which we draw the k map. So we'll come to the example for three variable k maps. So yeah, we can see that let's take a function f is equal to sigma 2 3 4 5. So first of all we will be drawing this table. X is in x represent both rows and y z represent each columns. So x is 0 here 1 and y z is 0 0 0 1 1 1 1 0, right? So f is a sigma of 2 3 4 5. What does this mean? So this function is 1 when m2 when it is m2, so and m3 and m4 and m5. So that is the meaning of this function. So when you have to like first we have to draw this box and then find where are m2 m3 m4 and m5, write once there. So after drawing this we'll be finding like so first 2 is there, so in m2 put write 1, then 3 is there, so m3 will be writing 1, m4 and m5 will be writing 1. So we wrote once, and now as same as in two variable k map, we will be clubbing this one. So first of all, like in three variable k maps, first we have to see if there are 8 ones which we can combine. So if there are 8 ones, the whole thing we can combine and put that if then 8 ones if we can combine, all the output will be one, right? So if all the boxes are filled with 1, the answer will be 1. So there won't be any x, y, z terms in the output. And if we can combine 4 ones, like here we will be combining 2 ones because there are no 4 ones adjacent to each other, right? So if we find 4 ones adjacent to each other, we can say that there will be only one variable changing. So we can write, say here 1 is there, 1 is there, and we find another one here, another one here. So we will be combining this 4 boxes, and the only changing variable, only unchanged variable is y, right? So this 4 boxes will combine and we will write y. So now we can only combine only 2 ones, right? Because we don't see any 4 ones or 8 ones combined together here. So we'll be combining these 2 ones and we'll be combining these 2 ones. So on combining these 2 ones, we will see like what is unchanged. See, we can see that x is constant for these 2 ones, and we can say that y is 1 here, y is 1 here. So x and y are unchanged, right? So we'll be writing x is 0. So first we write x dash, first write x dash, and here y is unchanged, so x dash into y. What are unchanged we have to write here, but when it's 0 we have to write x dash. That's the procedure for this schema. So for this one we will get x and y are unchanged, but x is 0, so we will write x dash into y. And the same way, coming to this box, we can see that the unchanged variable is x is 1 always, and the unchanged, another unchanged variable is y is always 0. So we can say that x is unchanged, x, we put x, and y is unchanged but it's 0, so we will be writing x y dash. Hope you understand. So this box represent x y dash, this box represent x dash y. We will be adding this both to get the function. We can see that how easily we will be getting these function. Like if it was in the case of SOP form, we will be drawing the truth table, and then for each and every one we will be doing multiplication of terms, and we will get 4 terms, and then we will have to simplify it to get this one. But this is a lot more easier for finding the uh, Boolean expression for this came up for this truth table, right? So this is why we are using this came up. So we will go to another example for this 3 variable came ups. So step 1, we will draw a table with x as rows and y z as columns. So x is first x is 0 here, y is 0, x is 1 here, and then y is 0 0 0 1 1 1, then 1 0. No, we should not interchange this. And first box we get as m0, then m1, then m3, then m2. So this is the thing we have to remember: m0, m1, m3, m2, then we get m4, m5, then m7, then m6. These both columns are interchangeable. So we will have this m0, m1, m3, m2, m4, m5, m7, m6. So we first draw this table, then we see the function. The function is 0, 2, 4, 5, 6. So the m0, m2, m4, m5, m6 are 1. So we have to put 1 in these corresponding minterms. So when m0 is 1, m0 is here, we put 1. M2 is here, we put 1. So m4, m5, m6, m4, m5, m6, we put here 1. So we draw the table and we put the ones. So now we have to combine them. So now see that are there any 4 ones together. The important thing here in K-maths is, like as I said, if you move from this box to this box, there is only one variable changing. From this box to this box, if you move, only there is only one variable changing. This also remains the same for these n boxes. So you consider them as like a cylinder or a sphere. So if we move from this box to this right, coming through this left, so this box, if we move from here to here, there is also the same as only one box is changing, right? So if it's like if you are going this way and coming through this way, so consider this as a sphere. So we can, like, you can move from up here and you can come down, come from this way. So we can combine these boxes this way also. So these ones and these ones combine, we can combine as 4 ones, right? So we will be combining these two and these two, so totally 4 ones. And then this one is remained uncombined, so we will be combining these ones. So there are two combinations, 1 2 3 4. This 4 will be combined together as one box, and m4 and m5, this will be combined as one box. So now we combine this two, right? So check what is not changing here. We can see that x is changing from 0 to 1 for these 4 boxes. and yz is changing from 100 to 10. We can see that z is not changing. Z is 0 here, z is 0 here. So like z is 0, right? So we have to write z bar. Z bar is like when so it will be 1. So z bar, we represent these four boxes as z bar. Okay, then we wrote z bar, right? Then we have to combine these two boxes. So what is not changing in these two boxes, m4 and m5? X is not changing, x is always 1, and z is and y is always 0. So y is always 0, so we will be writing y dash, and x is always 1, we will write x. So x y dash. So these two boxes can be represented as x y dash. So the function is x y dash plus z dash. So this is how we find the function for the function, we'll be finding the function for the three variable k maps using the uh, uh, k maps. So till now, is there any doubts? Maybe we can take a break for 5 to 5 minutes. 5 minutes. So we'll be having break for 5 minutes. Then we'll be continuing with four variable k map. Then we'll go and hands on in logism. We'll be making combination circuits in logism. That will be fun. So yeah, we'll start again at maybe we'll take 5 minutes break. Yeah. Okay guys, so we'll start again. Yeah. So we just finished three variable K maps. Is there any doubt till now? Yes. Is it clear? You can either put in chat or you can unmute and speak.
Sir, can you explain once again this output f is equal to xy dash and y? That's how we get the output.
What? Can you repeat? How we get x dash y dash?
Ah, x dash and
Here,
x
right?
dash is set.
This thing.
Ah.
Yeah. So we'll be combining. See the like the rule is first we have to combine 8 ones. If there are 8 ones, combine them. If there are 4 ones, combine them. If there are two, like if you find 4 ones, like see, you can say that this right corner, like as I said, from here moving here to here, there's only one variable changing, right? So z is changing from 0 to 1. So the same way, if you're moving from here to this way, like it's from going from back and coming here, you can say that y is changing. So we can also consider like like combining this way from here to from here to backwards. So if you can actually combine this way. So here are 2 ones and here are 2 ones, right? We can combine them and make us 4 ones. So we combine these 4 ones and see that what is not changing. See, like you can see that x is changing from 0 to 1 for these two, and from for these two, we can see that only z is constant. Z is 0, right? So uh, yeah. So yeah, this actually this box represent. Um, yeah. So wait, 1 second. Yeah, like don't consider this. So we'll be combining these four ones, and these 4 ones, like only z is not changing. So you see this is like z bar is there. So like combining these 4 boxes, only z is not changing, z is 0. So we'll be writing z bar, and combine these two, like this will be giving xy bar, because like here we can say that x is not changing, we'll be writing x. Like for these two one, x is not changing, like x is not changing, we'll write x. And for these two boxes, y is not changing but y is 0, so we'll be writing y bar, x into y bar. So this is how we find for x y bar, and combining these 4 boxes, we'll be getting z bar.
Sir, in this first case, like this x is not changing, no? In this, we will take the both m naught and m4 plus m4 and m5. Both we need to take are only two m4 and m plus m4 m5 we will take.
No, no.
Both things we will take.
For this two, we'll be taking m4 and m5 only. Like we'll be like all the four should be adjacent. Like we cannot take this
That I
value. We cannot
understood.
take.
That part
Yeah,
I understood. But what about this xy dash? We need to take only m4 and m5 or
yeah, m4 and m5.
okay. Thank you.
So I'll move on to four variable K maps. So from three variable K maps to four variable maps is like little bigger table, and so the rules will be the same. First we have to, like for from here we have to check if there are 16 ones possible. Like if all the boxes are 16 like ones, combine all them and see what is not changing. We can see that nothing is, like everything will be changing, so we will be putting one. If we combine 8 ones and see what is not changing, and we'll be writing the same like what we did till now, we'll be doing the same. So like how we will arrange this? So if there are four variables, right, we'll be like say w x y z are the variables. We'll be writing wx in for each rows and y z for each columns. So for wx, if you take wx, we'll be getting 0 0 0 1 1 1 1 0. Like the same way we should, like we rearrange these two columns, m0 m1 m3 and m2 and m3 we interchange, right? M3 and m2, the same way we'll be interchanging these two rows as well. So we see here like m0 m1, then m3 m2, this then m4 m5 m7 and m6, this already we know. But then not going to m8, this m8 will come to this column, like this row. So we'll be writing, first we'll be writing and then we'll be interchanging, because 0 0 0 1 1 1 should come first, then only 1 0 should come, right? So like so only we'll be interchanging this, then m6, then m12, 13, 15 and 14 the same way. Hope you understand, like so like if you have any doubt, you see this wx is 1 1, right? yz is 0 0. You combine 1 1 0 0. What is 1 1 0 0? 1 1 0 0 is a binary number for 12, so we can write m12. Like if you take this number 1 1 0 1, m 1 1 0 1 is 13. So like you write this 0 0 0 1 1 1 1 0 0 0 0 1 1 1 1 0, and write wx yz as a binary number. So 0 0 0 0 is a binary number, and if you convert into decimal number, you will get 0. Write m0. Like the same way, you take any box. Say we taking this box 1 0 1 1. If we combine 1 0 1 1, like what is 1 0 1 1? 1 1 is a binary number for 11, so we will be writing m11. So we can write what are the minterms to be set in this boxes by using this way also. So so this is the thing, like we have to change these two columns, we have to change these two rows. So this is how we will draw first the 4 variable box for the 4 variable k-maps. Yeah. Then coming on to example, so we'll learn how to find. See, this is the function. If wx yz is a function and the summation 0 1 2 4, what does this mean? So m0 is 1, m1 is 1, m2 is 1, m4 is 1, the same way like 14. So like so that is what this function represents. So first we will be drawing the box. We'll be writing x y and y z on this face. Yeah, wx as 0 0 0 1 1 1 1 0, y z as 0 0 1 0 1 1 1 1 0, and we'll be writing the minterms. So m0 m1 m3 then m2, the same way I told in the previous slide. We'll be writing all the minterms. So we'll be changing these two rows and these two columns. This to be kept in mind. And then we, after writing all, like we'll see this. First we will be drawing this table, wx and yz table. First we will write what are wx, what yz are there, and we'll be writing the minterms. So 0 0 0 0 is m0, 0 0 0 1 is m1, and like the same way come here 0 1 1 0 0 100 is 4, right? So 100 is 4. So you can, like that way we will write all the m terms here, and then we'll be writing this ones and zeros here, like this m's is a small m, this printing mistake here. So yeah, then like if f is, like we can see that m0 is 1, so write m0 is 1, m1 is 1, right here. There is no m3, right? So we'll be putting 0. M2 is 1, so we'll be writing here. So that way we'll be filling up the whole truth table, so whole k map. So fill this whole k map with zeros and ones using this function. So this is the third step or something. So after writing this, we'll be combining these ones. Like as I said, first check for 16 ones are there. Are there 16 ones? No, right? So there are no 16 ones. Check if there are 8 ones which can be combined. We can see that like these 8, this 8, this 8 we can combine, right? So this 8 we can combine, and then we can write the term for it. And then these three are not combined, right? So like we have to combine these two, like these three with maximum number of ones. Like we cannot like we combining these two and combining these two is of like not much of use. So like if we come, like as I said, going this right side and coming from this left side are equivalently like possible. So we can combine these two along with these two, say like here like this. So we'll be combining these two and these two. So we'll be combining these two along with these two, and we'll be writing 4 boxes. And the same way this two, like because this is not combined with anything, we'll be combining these two along with these two. So there is like totally 8 ones box and 4 ones box and another 4 ones box. So there will be 3 types. So like we coming on to this first this 8 ones box. This box, first we have to see what is not changing throughout the box. See, we can see that the whole wx is changing here, right? 0 0 0 1 1 1 1 0, the whole box wx is changing. So we forget about wx. Check y z. We can see that this 0 1 and 0 0, 0 is not changing. So we can see that y is not changing for the whole box, and y is 0. So when y is 0, we will be writing y dash. First write y dash. So for this whole box we wrote the term. And coming to this box, this m2, m6, m0, m4, these four boxes will be combining and will be writing the term for that boolean expression. So yeah, we can see that what is not changing. So we, for wx 0001, w is not changing, right? So w is 0 for both these like all the four terms. So we'll be writing w dash. First write w dash, and then coming to these two, check what is not changing. We can see that z is 0 and z is 0 for both of these like all these four. So z is always 0, so we will be writing z dash, w dash, z dash for this four boxes. Hope this is clear for this box. So coming on to this next box, m6, m14, m4, m12, check what is not changing. The same way, yeah, here we can see that 0 1 1 1 1 is not changing, right? For x is always 1, so we will be writing x first, and then checking for y z. Y like the same here, so z is 0, z is 0, so z is 0 for both the cases. We will be writing z bar for along with x. So that's how we get this whole equation. So first of all, what are the steps? I'll just say a recap. First, check if it's a 2 variable or 3 variable or 4 variable k-map. Draw the box accordingly. For 2 variable k-map, it will be like 2 by 2 square. For 3 variable k-maps, it will be 2 by 4 square rectangle. Then for 4 variable k-map, it will be like 4 by 4 square. And then assign like which represent rows, which represent columns. Write write wx and yz and write the following 0001 or 0, just 0 or 1. Write these terms outside this table and start to write the min terms, like what are these min terms, like m0, m1, m2, m3, like keep in mind that these two columns should be interchanged, because like moving on to this, only one term should be changed. So yeah, after m1, m3 should be there. The same way we have to interchange these two rows, and then we can say that write what are the min terms, and then see the function, write fill up these boxes with ones and zeros, and then combine these ones, like combine with maximum ones, like combine with 16 or 8 or 4 or 1, like try to combine these ones with maximum number. See that these two just we can just combine these two, but we have to combine it with maximum number of ones, so we will be combining along with these two ones. Like that's how we'll be doing. So combining with maximum number of ones, and then we see what is not changing throughout this box. Write what is not changing, and if it's 0, write the complement of this function. So that's how we will get this function. Hope 4 variable k-maps is clear to you. So are there any doubts? Tell me.
Sir, I have a little confusion.
Yeah. Tell me.
Three variable. So you said
Three
sir, in three variable. Here, sir, you told like only we need to consider M4 and M5 as a one pair.
Yeah.
Why not M0 and M4? Here in
We can consider. You can consider. That's not a problem. Like we can like we'll try to combine with maximum number of ones, right? So this one, and we can just combine with also this one. So m0,
it is already done in four variables, so that we have not considered, right?
Yeah, correct.
Okay, sir. Okay.
Yeah. Fine, right? Can I move on to combination circuits? So now we'll be doing it in logic. We'll be simulating circuits, and first we will be finding the truth. Like, okay, shall I move on? I'll explain. Any doubts? Okay, I'll move. Yeah, so building combinational circuits. So we'll be making combinational circuits hands-on. So first of all, we'll start with one example, one bit comparator. So what, like this is going to be like a circuit we are going to build. So we will be building this circuit. What it does is there will be two inputs, A and B. and there will be three outputs x, y, z, and this x will be 1 if a is greater than b, and y will be 1 if a is equals to b, and z will be 1 when a is less than b. But a and b are like just one bit, so like a and b can take only 1 or 0. So first we'll draw this truth table. So see, the a and b can be written as 0 0 0 1 1 0 1 1, right? So we'll be checking for each and every value. So a and b are equal for this term, right? So a is equal to 0, b is equal to 0. When a and b are equal, y should be 1, right? So this is equal, and like x is a greater than b, y is a is equal to b, z is a less than b. So here a is equal to b, so we'll put 1 for y, and for here a is 0, b is 1. Like we can see that b is greater than a, that so z should be 1. The same way here a is 1, b is 0, so a is greater than b, so we'll be writing x is equal to 1, and then a is equal to b in this term, so we'll be writing y is equal to 1. So is the truth table clear? So this is how we have to, like, whatever IC we are going to make, we will be writing inputs, all the possible inputs, and we'll be finding all the possible outputs for this x, y, z. So now we found the truth table. Now we have to find the expression, like how, like with what relation a and b, like with what relation we can find the x using a and b. So like for that we'll be using k maps. Till now, like we found no, right? How, like now we just found that how, like if we have a truth table or function, how to find the expression. So here, if first we will see for x, we can see that x is only 1 when m is 2, right? M2, this is m2, like 1 0 is 2, right? 1 0 is 2 in like binary of the decimal value of 1 0 is 2. So m2, so first we'll, like, this is two variable k maps, right? There are only two variables a and b, so we'll put a box, and we'll be writing this is m0, m1, m2, m3. We just said that m2 is 1, so we'll be putting 1 in m2. So there is only one, we cannot combine anything here. So this one, what is this one, like what is not changing in this one? Both a and b is not changing, but a is 1, b is 0, so we'll be writing b dash. So a b dash is the relation for this x. So this, like, we can represent this whole x as a b dash. The same way we'll be doing to y and z. For coming to y, we'll be drawing a 2 by 2 box, and we'll be putting ones in see here, like we can see that m0 is 1, and m3 is 1. So first we will draw a box and represent m0 as 1 and m3 as 1. So there are two ones, but we cannot combine them anyway, so as they are not adjacent to each other, represent this one as like a is 0 and b is 0. So we'll be writing a dash b dash, right? A dash b dash. Then this one here, both a and b are constant. A is 1, b is 1, so we'll be writing ab. So y is equal to ab plus a dash b dash. So this is the relation for y. We are using a and b as input. The same way we'll be doing for z. We can see that z is 1 for m1. Like ab is 0 1 1 means the decimal value is 1, so m1 is 1. So we'll be like, we'll draw the box m0, m1, m2, and m3. M1 will be 1. We write 1 here and find the relation. So we can see that a and b are same, like a and b are constant, but a is 0. So we'll be writing a dash b. So this is how we find the relation for x, y, z. So x is a b dash, y is ab plus a dash b dash, z is a dash plus a dash b. So hope it is clear. So we define what is one bit comparator. We draw the truth table using the what we said, like a is greater than b, x should be 1, y is, if they are equal, y should be 1, if they are less than b, z should be 1. Using that, we draw the truth table, and from the truth table we found the relation between AB and X, relation between Y, like we found the expression for Y's and Z's, and now we'll be going on to logician, and we'll be making this circuit. So I'll change, we'll go to logician. So I will open logician, like you guys can also open the logician, and we'll be doing it on a hands-on. So I'll start making the circuit. So for input, we'll be taking this add pin as input. We'll be just click on it and place it somewhere, and again click on it and place it below it. So A and B are two inputs, and then we'll be drawing two wires. So what we'll be doing is we have a long x, we have many inputs, right? X, Y, Z. So we'll be drawing a long wire, and we'll be taking inputs from these wires. Yeah, so first first thing, you can see that yeah, we'll be doing x as first. So x, the relation between x and ab is x is equal to ab dash, right? So first we will be finding ab dash. What is ab dash? This is a and this is b, right? So a and b dash. So we need an AND gate. We can go inside the gates column, and you can go to AND gate. Just click the AND gate and come here and place it. So ab dash, right? So connect the one end of an AND gate to the input a, and another input is b dash, right? So we need a NOT gate. We'll be converting b to b dash, and we'll be combining it to the NOT gate. So we need a NOT gate. So we can see that here in this position we have a NOT gate operator. Just click on it and place it on the end of the input of the AND gate. So this will invert the b gate. So combine this with this input of the b. So this will give the a b dash. So this will be the output. And for output pin, you click the right one pin, click it, and place it here. So this is the value. This will give us the value of x. Now coming to y, the relation is ab plus a dash b dash. So we have to make we have to combine gates, and we have to make ab plus a dash b dash. So the same, we'll be needing two AND gate, because we need ab and a dash b dash. So we'll be using two AND gates, and then we'll be using one OR gate, because we'll be like plus ab plus a dash b dash. So use two OR gate. So this AND gate will be like for ab. So combine it with a and another input with b. So this will give us the ab. You can combine this with the OR gate. Yeah, so this will give us ab, and it's combined with OR gate. Now we have another AND gate. We need to do a dash into b dash. So we'll be using another NOT gate. Put it in the ends of this AND gate. Take another OR gate and put in the inputs of the AND gate. So uh, yeah, so we can make the a dash into b dash using this gate. We combine with ab, so this will be a, and after NOT gate it will become a dash. This will be b, after NOT gate it will become b dash. We can make a dash into b dash, and this will be ab. So combined with the OR gate, we can make the ab plus a dash b dash. Yeah, so this will give us ab plus a dash b dash. Take another output pin, place it here. Yeah, so this is for y. We have done till x and y. So we will go to z part. Z is given as a dash b, right? So a dash into b. So we need another AND gate. We are multiplying two numbers, right? So use an AND gate. Keep it here. We'll be doing a dash b as we did a b dash in for x. We'll be doing a dash b. Take another NOT gate, and place it in the input of first input of AND gate. Combine with a, so that it will become a dash, and combine with b, so that it becomes b a, so it will become a dash b. So this will give us the output for z. Take the output pin and connect it. So this is the uh, logic circuit for the 1-bit comparator. So if these are the inputs, so here in label you can change the label as a, and then in here as b, and then this will be a greater than b. This is a is equal to b, and this is a less than b. So we can simulate and see. Go to simulate, pick the hand tool. This hand tool will make a simulate. So when we can see that a and b both are 0 here. So if if both are 0, a less than b is 0, a greater than b is 0, a less than b is 0. Only a is equal to b is 1, right? So this light green represent high voltage. Also it's written here 1. So if I change a to 1, we can say that a greater than b becomes 1. And if I change b to another 1, so both of them are 1, so it's equal, and so y becomes 1 again. So if I change 1 to 0, so b is greater than 1, we can see that this a less than b becomes 1. So this is the simulation for the 1-bit comparator. So this is how we make this 1-bit comparator. So any doubts in this 1-bit comparator? Yeah. So I'll move on to next example. So like the procedure is fine, right? So I'll teach in like the next example is majority circuit. So what is the circuit? So what it does is it takes three inputs as it takes three inputs and gives one output. The inputs are like the output depends on the majority what A, B, and C are taking. So if the majority is one, the output will be one. If the majority is zero, the output will be zero. That is this is the majority circuit. Will be clear once we draw the truth table. So here A, B, C will be writing A is zero, B zero, C is zero. So for the majority is zero, the output is zero. And for the next row A0, B0 and C0 is the same. 0 is majority, will be writing 0. And for next also same. So 0 is like there are two zeros, output is 0. And in the next two, there are two ones. So the output will be 1. And the next thing is like there are two zeros, the output is 0. Like what is majority will be shown here, like 101, the output is 1. Next is 110, the output is 1. The same way that all the if all of them are 3, all of them are 1, the output will be 1. So this is how we draw the truth table for the majority circuit. So we draw the truth table, right? Now we have to find the expression for x. So how we will be finding x using this ABC? So we'll be doing this through the K map. So first we'll be drawing 2 into 4 box for making this K map. As I said, like take A in the A is 0 and 1 in different rows, and BC as columns, different columns. Draw a 2 by 4 rectangle and write them in terms. This is M0, M1, M this is M3, then M2. So don't forget to change, like say 0 0 0 1, right? So 0 0 and here 0, then here 1. Don't and interchange it. Then after that 0 triple 1, right? 0 triple 1. We'll be writing what's there in the truth table with certain changes. So we draw the K map. Now we will have to combine this once. So you see if there are four adjacent ones. There are no four adjacent ones, right? Like if like we cannot consider this four adjacent one. We need a square of four ones to say that it's adjacent, four adjacent ones. So we can only take two ones as adjacent. So combine all these ones as two, like combine these two, combine these two, combine these two. So we'll be getting three terms. So considering this first green color combination, we can say that A is not changing for this green color. Also, C is always 1 for this green box. So A is 1 and C is 1. So we can write AC as one of the terms. Now coming to the red box, we can see that A is changing, but BC is always 1. So we can write BC as one term. Also coming to this term, the blue color box, A is not changing and B is always 1. So we'll be writing AB as another term. So this how we get the expression from the K maps from the truth table. So we can find that a value of x is AB plus BC plus AC. So this truth table corresponds to this expression. So we just found the expression using the K maps. Now as we find the expression for the value of x, we can go to logism and make this circuit. Yeah, so just go down and take a new page. So the expression is AB plus BC plus AC. So we will be needing 3 inputs. This symbol for input. Just click that and click here. Take 3 of them because we have 3 inputs. And then we need to do AB plus BC plus AC, right? So we need 3 AND gates. Go to gates, click on gate and click here. Click again another gate, click it here. Click another AND gate, place it here. So this is AB, ABC, right? So I'll just label it. In label you can go and you can write A. Here you can go and label it as B. And this you can go and label as C. So these are ABC, and we need to make AB plus BC plus AC. So so we'll be getting these 3 outputs, right? So like first we will be doing AB. Okay, first we will do AB. So we can combine this. So this AND gate contains A, and we'll be doing AB plus like we will be doing this AND gate will be corresponding to AB. So yeah. So this is AB. Now we need BC. So this AND gate represents BC. Now we need CA. So is this diagram clear? So this AND gate has connection of A and B. Yeah, is there any doubt? Yeah. So this gate is represents AB, and this gate represents BC, and this gate represents CA. So we need to add all of them. So we need an OR gate. So either you can use this as three, like we have 3 inputs and we have to add all of them. So we can change the number of inputs of this OR gate by going here. Number of input is 2. Click on it, delete it, and write 3. So this will make the OR gate has 3 inputs. So this AND gate will now we will be combining this output of this AND gates to the input of this OR gates. Yeah, so this AB plus BC, now we'll be doing CA. Yeah, so this will be giving AB plus BC plus CA. We will be take the output pin and combine it to the end of this OR gate. So yeah, so this output pin will be showing AB plus BC plus CA. I hope it's clear. So yeah, now A, B, C, all the 3 are like we'll start to simulate. Take the hand tool. Now A, B, C, all of them are 0, and the output is also 0 because the majority is 0. Now I am changing A to 1. The output doesn't change. I am changing just B to 1, no change. Just C to 1, no change. After C, I am changing any of the A or B. So I am changing A. The majority becomes 1, right? So the output is also 1. I am changing B and C. The output is 1. I am changing all A, B, C are 1. The output is 1. So this circuit shows the majority of A, B. Like if A and B are 1, still the output is 1. So if this like 1 is majority of ABC, so the output is 1. So that's how we get the simulation of what we just saw, majority circuit. So any doubts in majority circuit, please? Do you understand the assembly? Any doubts anywhere? I'll wait for 1 more minute. If there are any doubts, you can put it in chat or you can unmute and speak. Okay, so if there are no doubts, next example we are going to see is greater than 4 detector. So this circuit like will so this input, there will be 3 inputs A, B, C, but we'll be considering as these 3 inputs as just a one number with 3 bits. So this ABC is a binary number with 3 bits. So means like 111 means it's a 7. So the decimal equivalent of this binary number should be greater than 4. Then for the output to be 1, that is this circuit represent. So the output is 1 only when the decimal equivalent of the 3-bit input is greater than 4. That is this circuit. So as far as I said, we can like this 000 is 0, 001 is 1, 10 is 2, 11 is 3, 100 is 4. After 4 we will be having 5, 6, 7, right? All these 3 should be 1. So that is this truth table. The binary number is greater than 4, the function will be 1. You can make any, like you can okay, so with this one, with these 3 ones, now we have to find the expression for this function, right? So we just draw the truth table, and for the function we need, we draw the truth table, and then we have to find the expression for this corresponding truth table. So we will be using k maps for that. As we taught in the k maps, we have to draw a 2 by 4 table, and the rows, each row will be set as 0 and 1. First row is 0 and second row is 1, and the first, like all the columns are BC, like BC should be set as columns, like 0 0 is the first column, 0 1 is the second column, 1 1 is the third column, and 1 0 is the fourth column. Like we don't forget to, like 1 1 should come before before 1 0. So this will represent m0, m1, m3, m2. Then M4, after M4, M5, M7, M6, all of them are 1. So we will draw this K map using this truth table. Now we will be combining. If first we have to see if there are 4 ones. There are no 4 ones. Now we have to combine it with two ones. So combining these 3 numbers with 2 ones, combine these way 1 and combine these way 1. So there will be 2 terms in this expression. So combining these 2 1, we have what is unchanged here. A is always 1 in this 2, and also C is always 1 in this 2. Like this 2, C is always 1. Here is 1 and it's 1. So the term for this combination is AC. A is 1 and C is 1. We'll be writing AC, and combining these two ones, we can say that A is unchanged, and always you can see that B is always 1. Yeah, first is B, second is also B. So AB, so this 1 1 AB is unchanged. So AB plus AC is the function. So we found the expression using this truth table. Now using this expression, we will be making the circuit, and we will be seeing this greater than 4 is working. So yeah, till now, like this is the greater than 4 detector. So if you take any function, first draw the truth table, and find, like for the output, draw the k map, find the expression, and using this expression we'll go to logism, and we'll make the circuit. We went to logism. I'll take another page. So here we'll be doing the greater than 4 circuit. So there are 3 okay. So yeah, this is the input pin. Take 3 inputs because we'll be having 3-bit number. I took 3 inputs. Yeah. Then the expression for this function is AB plus AC. So we'll be doing a logic circuit for AB and AB plus AC. I'll just label them as A, this as B, and this as C. So we need to do AB plus AC, right? Yeah, AB plus AC for the greater than 4 detector. So AB plus AC, we need 2 AND gate, and we will be combining the outputs of this 2 AND gate to an OR gate. So first we will take in 2 AND gates, one for AB and another for its AC. So AB plus AC, yeah. Take A and wire of A to combine with AND gate. Then we will be doing B. So this AND gate will be representing AB, and now we have to do AC. So this will be connecting one end to A, and another is connected to AC. So this represent AB, this represent AC. Now we need to combine it the OR gate. So output of this AND gate, combine it here. Output of this AND gate, combine it here. We will be getting OR gate of AB and AC. So this is AB AC combining with AB plus AC. So this will be the output coming with output pin. Yeah, so we have built the circuit. So if all the inputs are 0, so A, B, C is 0, the output is 0, and if we change to 0, so this I'll start to simulate. Take the hand tool. So ABC is like ABC is 0, so the decimal number is 0. If I change C to 1, the decimal number is 1. Now B1 C0 is decimal number is 2. If I change C to 1, it will be like decimal numbers 1 1. What is 1 1? It's 3, right? Now we will be changing to 4, like B0 C0 1, A is 1. So A is 1, BC is 0. It represents 1, and from now on, if I change C to 1, you can see that if I change C to 1, the number becomes 5. 101 is 5, right? So from 101 is 5, so the output is 1. Now if I change 110, it's the decimal number is 6, and now it shows 1. And if I change C to 1, all of them are 1, and the output is 1. So that's how, like if the numbers greater than 4, the output is 1, and for the numbers less than 1, less than 4, the output is 0. So this is the logic circuit for the greater than 4 detector. So like these are just some examples. So if you have any ideas in your mind, so if there is a 3-bit number and you have to find like which is greater than 3, greater than 3 you can do, or anything, like whatever function you have you can make. So the procedure is like we have to draw the truth table and find the output, and output you have to find the expression using the k-map. With the expression you can come to logism and simulate and see. So this will be the building block. So this is how we should do for any of the functions. So are you guys clear with this logism simulation part? Any doubts, you can put the chat, or you can unmute and speak, say. And so after this, Delia will continue the Verilog part of this session. So, any doubt?
Sir, here we are getting the true as per truth table, no sir. Whatever the majority of there, the output will we are getting the same, right, sir?
Yeah, yeah. 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 Hello. So Delia can continue if there are no doubts.
So let's see what is Verilog. Today we'll just see what Verilog is. We'll just see about the introduction. Why do we need Verilog? So in the world of digital system, when we have logical circuit everywhere in our devices, like apart from building a logical circuit, we also have to check and validate the given circuit, like whether it's giving a correct output for the possible, like we need to check all the possible inputs as well as the we need to verify whether the outputs are correct or not. For the smaller circuit, which involves like fewer components, we can do it manually. We can just put input the values and we can check manually whether the circuit is giving correct output or not. But as soon as the complexity of the circuits increases, as soon as the circuits become more complex, uh, we can't do it manually. So we have a tool, we have this power of computation called as Verilog. So what is Verilog? Verilog is basically a verification. It stands for verification plus logic. It's an hardware description language. It's an kind of a programming language, which uh, which is basically used to validate any given circuit. So like we have two parts in Verilog. One is a design, which is the designing the digital system, and the other one is to test and validate the digital system. For in the first one, we'll design the circuit, we'll design the combinational circuit, and then the other one will test and validate the digital systems. We'll use this EDA playground for the Verilog. Like you just need a browser for this. That's it. Yeah, and that's it for the day. So, guys, do you have any doubt in the today's session? You can just ask. You can just unmute yourself and ask. Minimum SOP and POS. Okay, just a minute. You mean this thing, SOP and POS? Unmute and tell.
Yes, madam.
So you want me to explain? You want me to explain this expression from the truth table again?
Yes, ma'am. Yes, ma'am.
Yeah. Okay. So basically, you have some function f1 whose value is 1 when x, y, z are correspondingly 0, 0, and 1. It is 1 when the values are 1, 0, 0, and again 1 when x, y, z are 1, 1, 1. So to find what f1 is, to find the expression Boolean equation of f1 in terms of x, y, and z, you will write the mean terms corresponding to this terms where f1 is equal to 1. So you will get for mean terms, when the value is 0, we'll use primed variables. So the mean term corresponding to this term is x prime, y prime, z. Similarly, the mean term corresponding to this one will be x, y prime, z prime. For this it will be x, y, z. Now to get the function f1, we'll take an or operation between all these mean terms. So the first one we got as x prime, y prime, z. Then we got x, y prime, z prime, and then x, y, z. We'll add them. That is, we'll have an OR function between them. So correspondingly, this term is equivalent to M1, this is equivalent to M4, this is equivalent to M7. So this is a standard of brief notation. To write this thing, we'll write it as summation. Whenever there is summation, just remember you'll have small m, which is a mean term. So you will have the summation of mean term corresponding to first, fourth, and seventh term. Similarly, to get f1 in terms of POS, this is product of sum. To get this, we'll find the terms where this f1 is equal to 0. So it is 0 at the first position, I mean at the 0th position. So corresponding to this, min term is x prime, y prime, and z prime. Corresponding to this 0, it is x prime, y, and z prime. Similarly, find the mean terms corresponding to all the zeros. Now you will get an expression for an f1 prime as this. Whenever you will do the OR operation between the zeros of the function f1, you will get f1 prime, but you want f1. So why are we using this? Just we know that complementing the and thing will give you OR, and that is what we want in the POS form. So we'll just complement it by using De Morgan's property, like complement both the side. Complementing on LHS, you'll get F1. On RHS, you will get complement of this into complement of this into complement of this, and so on. So complement of this whole thing will become complement of x prime. There is an AND operation between this that will get converted to OR. So you'll get plus. Then complementing y prime will give y. That is multiplication or AND operation will get converted to OR, and z prime will get complemented to z. And this OR will get complemented to AND. So basically, all the primed will get complemented to the normal variables, and all the normal variables will get complemented to primed. And will change to OR will change to AND. This is what De Morgan's theorem says. So this expression will be product of sum. This will be sum of product. Did you get it?
Yes, ma'am. Thank you, madam.
Yeah, fine. Any more doubts, guys?